So for our next talk, we're very happy to have Kohanda from UCLA, who will tell us about convex hypersurface theory in higher dimensional contact topology.
Okay, can you hear me?
I hear you.
Hello. Okay. Anyways, thank you very much for the invitation to speak. Amazingly, today in Southern California, it's cold, so that's why I'm wearing a sweater. Okay, so today I'd like to talk about convex hypersurface theory in higher dimensional contact topology. And I've given this talk several times, so if you've heard me speak about this, there's nothing new in here. This work is joint work with Yang Huang, who I think is the moderator, who will answer all the basically, if you have any hard questions, you can ask him. Hard technical questions you could ask him. And the other thing is he's actually looking for a tenure track job for next year. So please keep that in mind. Oops, sorry, I did this wrong. Okay, so the goal is the following. Given a closed co-oriented contact manifold MC of dimension 2n+1, so today our ambient contact manifold is, I think, always going to be 2n+1 dimensional. So the contact structure is given by a global one form alpha, such that alpha wedge d alpha to the power n is always some sort of positive function times a volume form. And the goal is to cut it up. Basically, what you'd like to do is cut it up along closed oriented hypersurfaces in order to analyze it. So somehow you have some sort of n manifold, and you want to somehow keep on, find a surface, or sorry, find a hypersurface, chop it up, find another one, chop it up, and have small pieces, and then analyze each piece and put them back together. And amazingly, this kind of thing was actually not available. So for contact 3 manifolds, convex surface theory has been a very useful tool for decomposing, analyzing, classifying contact structures, and especially tight contact structures. And surfaces are pretty abundant in 3 manifolds, and even things that are compressible. So, have surfaces that are incompressible, meaning it is pi1 injective. Those things are interesting, and even things that are not that are compressible are actually interesting. So you can use surfaces to somehow sweep. You can sweep surfaces around the 3 manifold, and you garner some information. So this has been pretty successful, and for much of the around 2000, there's a lot of activity. The question is, what can you do in higher dimensions? Oh, I guess I didn't tell you the answer. The answer is, for the time being, is that you can do quite a bit, but there's still a lot you can't do. Okay, so for a while I have to do some symplectic preliminaries. So if you've never seen this kind of thing, it might be a little bit of hocus pocus. So symplectic and contact preliminaries, and it might seem a little bit dry, and you can sort of sleep through it if you either already know it or you find this a little dry. And then we'll come back, and it might be a little bit more interesting later. So hang in there. So a pair consisting of a 2n dimensional manifold and a one form lambda. So the W is a compact manifold with boundary. And lambda, a primitive of a symplectic form, is called a Liouville domain if the vector field defined as such, the interior product of x and d lambda is equal to lambda. And it points out about the boundary of W. So this x is called the Liouville vector field. And one of the most interesting things is the behavior of this Liouville vector field. Or maybe slightly more precisely, what the Liouville vector field does up to homotopy. So the Liouville, a Liouville domain could be pretty complicated. So I'm going to schematically draw them as, the Liouville vector field is this, meaning the dynamical behavior can be as pretty complicated. And in particular, you can have things like things things that look like Cantor sets. The set of orbits can look like Cantor sets. Okay. In contrast, if you're interested in a nice Liouville domain with nice dynamics for X, then you consider things that are called Weinstein. It's called Liouville domain is called Weinstein is if X is gradient-like for some Morse function f from W to R. And in particular, it has isolated Morse-type singularities. One thing is that because you have the condition that the Liouville vector field pointing out of the boundary of W tells you that this thing is contact. The boundary of W together with the contact form, the one form restricted to W is contact. Oh, one more thing. If you have any questions, please feel free to ask. Okay. Okay, so now some contact preliminaries. Closed-oriented embedded hypersurface of dimension 2n inside a contact manifold of dimension 2n plus 1 is convex if there exists a contact vector field B which is transverse to sigma. So a contact vector field is a vector field. Okay, it's such that if you integrate the vector field, you get a contact diffeomorphism. And the condition, which is very strange and somehow works, is that V be transverse to sigma. So you have sigma and you want V to be transverse to it everywhere. Oops. Sorry, I'm having some scrolling issues. Okay, its dividing set is the set of points in sigma. It's a subset of sigma consisting of points such that V of X is in the contact structure C. So the way to think about it is the following. The hypersurface has codimension 1. You can think of it as surface instead. And then the contact structure also has codimension 1. And generally, they're sort of wobbly. Contact structures are wobbly things. So they sort of wobble around. And you're interested in the place, set of points where the contact structure is going to be perpendicular to the hypersurface. Okay. So, and what do we mean by perpendicular? It's with respect to this contact vector field V, which is transverse to it. Okay. And so we have this strange set where you have this perpendicular condition, and there's no reason to, if you've never thought about this before, there's no reason to think that this gamma is of any interest. But it turns out that gamma is a contact manifold of dimension 1 lower. So it's a hypersurface inside sigma, has dimension 2n minus 1, and up to isotope. Oh, a contact manifold is a manifold such that if you restrict the a contact submanifold is one such that if you restrict the contact structure to this submanifold, it stays contact in 2 dimensions lower. And up to isotopy, gamma is independent of the choice of contact vector field. And gamma divides sigma into alternating positive and negative regions R plus of gamma and R minus of gamma, which are Liouville with respect to the restriction of alpha to these like 2 subdomains, where alpha is a contact form for C. So we have this. Do I want to draw? Or maybe I should first draw some picture. So schematically, you should think of something like the following. You should think of, you have a region like this. This is sigma. And then the dividing set is like this. Basically, mentally, this is what I always keep in mind. Okay. Oh, the question is this dividing set necessarily connected or not? In dimension 3, generally it's generally there's no condition on whether it's connected or not. In higher dimensions, if it's Weinstein, then it has to be connected. If the R plus and R minus of Weinstein is connected. For Liouville, there are examples where it's disconnected. Okay, and one of the things is that I have to have a special definition called a Weinstein convex hypersurface. Convex hypersurface sigma is said to be Weinstein convex or Weinstein convex if R plus minus are Weinstein. So in this particular case, which is basically all the most of the convex hypersurfaces we'll deal with will be Weinstein for today. So the boundary will be disconnected. The dividing set will be disconnected. I'm sorry, the dividing set will be connected. The characteristic foliation sigma C is a singular line field in C intersect T sigma, such that this interior product of the characteristic foliation and D alpha of this restriction is equal to 0. So this means the following. So remember, like you have C and you have sigma and you have C, and generically they intersect in something of dimension 2n minus 1. Is that right? Okay, so the sigma has dimension 2n, C has dimension 2n. They're both sitting inside a 2n plus 1 dimensional manifold. So they generically intersect along something of dimension 2n minus 1. Okay, and you now consider, so that's C intersect T sigma, and D alpha wants to be as symplectic as possible. So that means that, well, it's maximally non-degenerate, which means that there's actually one direction that's still in the kernel of this thing. Okay, so basically the characteristic foliation is one direction, which is in the kernel. The good thing in dimension 3 is that this characteristic foliation is just, since you have like low dimensions, the characteristic foliation is simply C intersect T sigma. And maybe the most important remark here is that the Liouville vector fields of R plus minus are actually tangent. They direct the characteristic foliation. So you can really think about, you know, a convex hypersurface as being two Liouville domains stuck together, and the characteristic foliation is the Liouville vector field on one side and Liouville vector field on the other side. Maybe you have to reverse orientation, reverse directions. Okay, again, I have some. Okay, let me explain a little bit about what's known in dimension 3. So the following are known. A C infinity generic surface sigma is convex. The neighborhood of a convex surface sigma is determined by the oriented embedded one manifold gamma. So in this case, if you have a convex surface, then its neighborhood is completely determined. So you might actually have slightly different looking characteristic foliations in a neighborhood, but the contact topology is completely determined on the neighborhood of this convex surface. And so, yeah, so manipulating convex surfaces basically reduces to manipulating curves on surfaces. Now, a C0 generic one parameter family sigma cross 0, 1 embedded in M. So suppose you have something, you have a surface and you sort of sweep it out in M in an embedded way. Then this thing is convex except at finitely many times Ti. And the dividing set changes at these sort of the singular moments or bifurcation moments by a bypass attachment as we cross this Ti. So this is like the left-hand side is before and the right-hand side is after. Before, and then the red things are portions of the dividing set. Okay. Okay, I think I won't answer the comment. It seems sort of difficult. Okay, so the left side is the right before Ti, and the right-hand side is right after Ti, and the red set is part of the dividing set. So as you go from left to right, the dividing set gets modified like this. It's some sort of like, a sixth, or is it a third rotation? You rotate, maybe like a sixth rotation. You just rotate like that. What happens in so anyways, the point is the following. Oh, maybe I should go back. The point is, what you pick some surfaces. It actually could be sort of trivial looking, like solid tori that that are sort of tubular neighborhoods of knots, right? And you can sort of like spread it out and use it to sweep out the three manifold. And as you sort of sweeping out, you have some moments where you have bifurcations and so on. And if you analyze this, it becomes some sort of topological problem. And this way you can study contact three manifolds. Okay, and what can you do in higher dimensions? So a closed hypersurface so there's theorem A and B, and then maybe there's something else that's related later. A closed hypersurface in a contact manifold can be C0 approximated by a Weinstein convex one. So you pick any, someone gives you a closed hypersurface, and I can, wiggle it, although in a C0 small way, and then get something that's Weinstein convex. This one also comes with a pair. If you have a contact sector C on sigma cross 0, 1, such that the hypersurfaces sigma cross 0 and sigma cross 1 are Weinstein convex, then up to some sort of boundary relative contact isotopy, some sort of contact isotopy which fixes the boundary. So you have two choices. You can either wiggle the sigma cross T, or I can wiggle the contact structure. And here I'm just wiggling the contact structure in the way it's described. Then up to a boundary relative contact isotopy, there exists a finite sequence T1 ... Tn, such that the following hold at all the moments except at Ti, sigma cross T is Weinstein convex. And for each I, there exists a small neighborhood such that C restricted to this sigma cross Ti minus epsilon cross Ti comma Ti plus epsilon is contactomorphic to a bypass attachment. There's some sort of higher dimensional analog of a bypass attachment as well. So anyways, so it more or less gives you a reasonably complete description of the kinds of things you want to do. Okay. So at any rate, Theorem A tells you that given some random hypersurface, you can now arrange it. After wiggling a bit, you can arrange it so you can cut in a nice way and analyze the pieces. So these are sort of having a contact manifold with this convex boundary is one step towards understanding sort of pieces of contact structures. Okay, so what is a bypass in higher dimensions? I'm not sure if this description is particularly useful, but I will say it anyways. So a bypass along a convex hypersurface is some sort of topological sort of smooth version of some sort of topological operation. And the is a contact version of a smooth operation. So I called it topologically canceling, but it's probably more better said as smoothly canceling pair. So it's given by attaching a smoothly canceling pair of middle dimensional handles. So the middle dimensional handles are n handles and a canceling n plus 1 handle. So this thing here, right. Oh, the color is not so good. This is supposed to be an n handle, and then you're now attaching a canceling disk, okay, which is an n plus 1 handle. So let me just erase that again. So because okay, so that's in dimension 3. You attach a 1 handle and a canceling 2 handle. Okay. And the data consists of d plus, d minus, which are Lagrangians inside. This is r plus. Sorry, this is r minus and this is r plus. You take a Lagrangian disk inside r minus and another Lagrangian disk inside r plus. with Legendrian boundary, basically. And the setup is such that, oh, I think I want a different color. Let's use purple. Okay, so the setup is such that inside the boundary, inside the dividing set, the boundary of R plus, R minus is lambda minus, and the boundary of, boundary of D minus is lambda plus, and then boundary of D plus, D plus is lambda plus, and then you have a short braid chord from lambda plus to lambda minus. So that's the situation. And so anyway, so the end handle is going to be attached to lambda, to gamma along this strange looking sum. And the sum, this is one of these things I can never remember, but I think it's this. Okay. You have these two things and you sort of do some resolution. And I think this is, oh, no, it's the other way. I think it's probably, let's say, I think it's this, but it might be. Yang can correct me. Okay, so we have something like this, and you attach the end handle, so Lagrangian end handle along lambda minus some lambda plus. Okay, and then you attach some sort of n plus 1 handle. Anyway, so once you do this, the new R plus is obtained from the old R plus by removing the neighborhood of the D plus and attaching an n handle along this thing. And then the new R minus is obtained from the old R minus by removing a neighborhood of the D minus and attaching an n handle along this new Lagrange. So you remove something, you dig a little bit. So the first step in this digging is like you dig. Okay. And then you attach something along here, and it changes the topology a little bit. Okay, are there any questions? Are you sure? Okay, in that case, we'll proceed to a sketch of the proof of Theorem A. So in step 0, what we do is the following. The first thing to notice, we have to do some preliminary stuff. So the singular points of the characteristic foliation occur when the contact structure is tangent to the hypersurface. So it happens when T sigma is equal to plus or minus C. And if the signs agree, then we say that the singular point is positive, and otherwise the singular point is negative. Okay. A C infinity generic hypersurface has isolated Morse type singular points. I don't care, for the moment, I'm not concerned about the dynamics, but I'm just talking about neighborhoods of singularities. So you can take a C infinity small perturbation and make sure that the characteristic foliation has isolated Morse type singular points. Okay, and then after a choice of orientation of vector field directing this characteristic foliation, the positive singularities have index 0 to n, and the negative singularities have index n to 2n. This is sort of analogous to the fact that if you have a Weinstein domain or a Stein domain, then, and you're interested in the Morse decomposition, sort of Morse handle decomposition of such a thing, then if the manifold is 2n dimensional, then you only have indices up to index n, critical points of indices up to n. This is basically this statement. So okay, and hypersurface sigma is said to be Morse if this is gradient-like for some Morse function on sigma. Okay. And it is Morse plus if, in addition, there are no trajectories from gamma sigma from a negative singular point to a positive one. So generically, yeah, so generically this, you have Morse and actually Morse plus. Okay, so if you have something that's gradient-like, you can perturb it so that there are no trajectories from a negative singular point to a positive one. And in the case that's sort of in most, somehow the thing that's in question is really if you have a negative singular point to a positive singular point and they both have index n. Okay. And right, so remember all the critical points can be made, like the positive ones can be made to have indices 0 through n, and the negative ones are higher or n and higher. And one of the weird things that could happen is that you can have an index n singular point, critical point, to an index n negative critical point to an index n positive critical point. Okay. And this doesn't happen in a generic Morse for a generic Morse function, but it could happen for a one-parameter family. And Theorem B concerns one-parameter family. So this is something that's important in a one-parameter family of Morse functions. Okay. And the following is some sort of Morse function recognition lemma. It's some sort of exercise. And a smooth vector field V on a closed manifold M is Morse if and only if the following hold. First of all, V is Morse on a small neighborhood of its zero. So at least locally, it looks like a Morse gradient. It's gradient-like respect to a Morse function. And secondly, for any point in M where the vector field is non-zero, the flow line passing through it eventually limits to V and forward, limits to a 0 in forward and backward time. So you have something like this. You have a point X, and you want to eventually get to a critical point. Maybe I should have called it, maybe it's called X. It should get to a critical point, I don't know, some Xi, and it has to come from another critical point, X sub j. So that's condition 2. And then condition 3 is that there are no closed cycles. You can't have things that look like that. Yeah, so having a closed cycle is really a sort of obviously a problem. And as long as the obvious problem doesn't exist, you can write down a Morse function. Okay. And the statement is that any Morse plus hypersurface sigma is Weinstein convex. So if your characteristic foliation can be given this Morse plus condition, which is not so hard to check using this lemma, then it's Weinstein convex. Okay. And the proof is similar to Giroux's proof for convex surfaces in dimension 2 from like the early 90s. Okay. So next, I'd like to sort of give the basic idea in dimension 3. This one's actually sort of hands-on and it's reasonably pretty. Oops, what is this? Oops. Okay. And the proof in dimension 3 is reasonably amenable to higher dimensional generalization. So we choose a contact form dz plus e to the s dt on R3 with coordinates stz. This is a slightly unusual looking thing, and I guess it makes sense only for, does that make sense? Yeah, anyways, it's contact, you have a contact form like this. And we consider the surface sigma equals z equals 0. So my hand is going to be the xy plane, and this will be the z direction. Okay. And so anyways, this is the surface. And and the contact structure is going to be doing the following thing. It's called the propeller picture. So the contact structures will be sort of always tangent to these, the DDS direction, and it will start rotating like this. Okay. And as you go towards the positive S direction, it gets steeper. Okay. This is a thing to keep in mind. That's this contact form. And what we'd like to do is perturb sigma to put in many sources and sinks. So somehow the disappointment probably for dynamical systems people in the audience is that the goal is to get rid of the dynamics and it becomes Morse theory. So the goal is to somehow destroy the dynamics so it becomes Morse theory. Okay, so the first attempt would be to do the following thing. Suppose you have, this is basically in the previous picture, it looks like DDS. Okay, is to apply the Giroux elimination lemma to create a pair consisting of an index 0 and index 1 singular point. So you have, you can do some sort of contact version of this. Okay, but then you sort of notice there's something not so good about this, right? So you have some curves here. If you think about dynamics, you start here and you sort of like get sent out a little bit, a little bit far back. Sorry, a little bit to the side. And when you do this kind of operation, things can go very bad. So I really don't like this. On the other hand, what you can do is you can simultaneously create 4 critical points. So one of index 0, I can't remember, this is like 0. You have like a pair of hyperbolic points and you have an elliptic one. Okay. If you simultaneously create something like this, then you notice that you have this interesting dichotomy. You either enter and you get sucked into a critical point, or the only thing that matters for things that don't get sucked in are you can arrange it so that if you start here and exit, the holonomy when you sort of enter versus where you exit, like nothing happens. You can arrange it so that things that go in get sucked in, and then things that go through just go through and as though nothing happened. So these things are called plugs, right? Things of this sort of form are called plugs. Okay, so that's what we'd like to do. So in 3 dimensions, you can geometrically realize this using something called the mushroom. The technical term of the paper is called C-fold. Anyways, probably the working name for this is mushroom. I guess I've made this joke already, but in these unfortunate COVID times, obviously putting a lot of these mushrooms looks like a coronavirus. So anyways. Okay, so the mushroom is something like the following. So remember the contact structure sort of rotates like this. So front face is like S smaller. This is smaller S. And this is larger S. Okay. And when you go from smaller S to larger S, you do this. So in the front, it's sloped a certain way. And in the back, it's sloped a little bit more. And so the front face and the back face have these like slanted characteristic foliations. And the other faces, so R2, as I said before, has characteristic foliation that looks like DDS. And then actually the top face has DDS, and the sides also have DDS. So the only thing non-trivial are the front face and the back face. So you have to slightly convince yourself of this, but that's what the dynamics looks like. Okay. Now, if the base of the mushroom is sufficiently thin, so base is like the thin means like if this is sufficiently thin. Oh, but maybe I'll just say like the width of the mushroom is what you think it is. It's somehow the distance from the length here. Okay. So the width is somehow the maximum sort of width that you can fit this in, or the minimum width that you can fit in with something like a caliper. And anyway, so the size of the base is this length. Okay. And if the base of the mushroom is thin, then let's look at the trajectory. So you go in here and you go up, oops, sorry. It's exactly like it's drawn. It goes up, right? Goes across, and then comes back down, right? And the thing to remember is that it's the side, on the far side, it's sloped more. So what we'd like to do is that make sure the base is narrow enough so that when you go around, you start, if you follow your path, you end up on the side. And then you sort of, once you get to the side, you sort of spiral around and eventually end up at this edge. So anything that sort of comes in from here, so it goes up, goes back, and then sort of eventually ends on this edge. Okay, so basically this is the point. So anything, basically most of the front edge of the mushroom gets sucked into this sort of singular locus. You can smooth it, so it's actually you have a pair of critical points, and it looks in this way. It acts like a plug. Okay, and quantitatively, you have to do this calculation. The width of the mushroom has to be slightly more than twice the width of the base. So there's actually a mildly quantitative feature to this. So the profile of the mushroom looks like this, and this was the width. I'm sorry, this was the base. And this was the width, right? And the width actually has to be slightly more than twice the length of the base. Okay. And what we'd like to do is, like, if you have some orbits coming in, you'd like to block everything, right? So you'd like to block everything. So this is the DDS direction. Oh, sorry. Yeah. So you want to sort of arrange the mushrooms as tightly packed as possible. So you do something like this, and these things get blocked, basically. Okay. And then you need to put in like rows of mushrooms, and from this like quantitative statement, you can just arrange 3 rows of mushrooms. You have something like this. This is now the DDS. This was the profile. This is now the DDS direction. Let's use, I don't know, something like this. Oops. We put mushrooms like this. And then the second row overlaps a little bit with the first row, but can't get rid of everything. And then the third row, we have sort of sucks in whatever's left over. So you have, you need 3 rows of mushrooms. And the point is that these mushrooms can be made arbitrarily small. So but the width to base ratio is still the same. You can make these smaller, as small as you want, and then the blocking ratio is still the same. Okay, so this is how you yeah, this it's probably pretty clear by now. This if you have any kind of dynamics on a surface, you can completely destroy it, and it's a very flexible operation. So you can just sort of destroy your dynamics as you would like, and this proves theorems A and B in dimension 3 in a relatively efficient way. Okay. All right. So what about mushrooms in higher dimensions? So the first thing I should have that you need to know. Oops, this is probably the first thing you need to do. You need to know is that so if you have your characteristic foliation, okay, and you have something that's transverse to it, so you have a surface, let's call it Y, of this is inside. This is something transverse to a characteristic foliation in dimension 2n, right? The hypersurface is dimension 2n, and if you have a vector field and you have something transverse to the vector field, then it has dimension 2n minus 1. And anything that's transverse to characteristic foliation is actually contact, right? This is actually sort of a nice fact. Anything transverse to characteristic foliation is contact. Okay, so what we'd like to do is like do the higher dimensional analog of this, except now you have like a slice which is contact, right? Instead of having things that look like DDT, right? Now it looks like now it looks contact. So the contact form is dz plus e to the s beta on R2 cross y2n minus 1, and the hypersurface is again this with characteristic foliation DDS. Now you take a contact, the profile previously, so in the previous case, right, the profile was just, the contact form dt. in dimension 3. In higher dimensions, the profile, the thing that's transverse, is a contact form. Oh, sorry. Yeah, let's call it. It looks the profile, namely the portion that's transverse to the DDS. So this is transverse to the DDS. Is called a contact handle body, and it's modeled on the following thing. It's DDT. So this is the DDT direction, and you have coordinates 0 to T0. And then this direction is Weinstein. And this is, okay, so now you have to worry a little bit about the dimensions. So this is W2n minus 2. Is that right? Yeah. Okay. So, and then H has dimension 2n minus 1. It's a little bit annoying that so you have to worry about these like dimensions. But so then you have something like this, and you try to apply the same sort of procedure. And I'll just quickly tell you, if you make an analogous mushroom, then what happens is the following. What happens in terms of dynamics is that if you're sort of somehow squat in the middle of this, if you flow right in, then you get sucked in, and then if you're a little bit near the bound, everything that's in the interior basically gets sucked in. And if you're on the boundary, you actually get sort of pushed around like this. The flow is sort of like this. You're going from the singular, you flow basically along the characteristic foliation on the boundary. So maybe I'll say that a little bit more. So the context, the mushrooms can be constructed so that they look like three-dimensional mushrooms cross W, with some damping out near boundary W. This is actually sort of a technical issue, which is important. And all the trajectories that enter the handle body, right, minus a small neighborhood of the boundary, flow into some sort of singular point. But then the characteristic, basically the point is on the boundary, so we have the stalks on the boundary, you actually always flow from the positive side to the negative side along the characteristic foliation. There's actually some sort of thing you have to worry about, which gets moved around a bit. Now, at this point, the thing to do is actually prove more at the same time. So what we're going to do is by induction on the dimension, and in each dimension we prove a host of other statements. So let's say okay, including the next one. So you prove a host of statements in dimension 2n minus 1 before going up to dimension 2n plus 1. So, and then the theorems, the thing you have to prove are actually sort of complicated. There's a lot of things you want to prove in dimension 2n minus 1 before going up. So the following is also something you want to prove in dimension 2n minus 1. So any closed contact manifold admits a compatible open book decomposition with Weinstein pages. Okay. And also any compatible contact manifold Weinstein, if you have a contact manifold with Weinstein convex boundary, you have a compatible generalization of an open book called a partial open book decomposition with Weinstein pages. So the first statement was proved by Giroux using Donaldson's approximate holomorphic technology and the work of Ibort, Martinez Torres, and Presas. And the thing is, we don't really want to do this because you have no idea how you get these things. And at the moment, the second statement cannot be proved using the Donaldson technology. So strangely enough, right, you don't really know how to prove this item number 2 using the Donaldson technology. So anyways, you want to prove all these things using our sort of technology in dimension 2n minus 1, and then going up to dimension higher. Okay. So suppose you have this is the transverse section, Y. Suppose you have a contact manifold dimension 2 boundary, which is transverse to its characteristic relations like this. By the inductive assumption, we assume that the boundary of Y is convex after a singular small approximation. So right. So you're doing something in lower dimensions. So like we assumed that we could do this in 2n minus 1 dimensions. So the boundary can be made convex, or sorry, convex with Weinstein convex using sort of the inductive assumption. Okay. So we make the boundary convex, and then y can be given, the whole of y can be given the structure of partial open book decomposition. Okay. And then I'm going to explain what happens when you have a genuine open book decomposition. The schematic picture of an open book decomposition is the following. You have an open book decomposition of a manifold is like a decomposition. You have M, your manifold, maybe it's called Y, is Y. Okay. And then you take away this thing called the binding, which is the point in the middle, right? Which is a contact submanifold. Okay, contact. And then the rest has a projection to S1. So you have the Y minus B fibers over S1, and then these are supposed to be the pre-images of this map. So this is, I guess, call it pi, and these are pi inverse of theta. Okay, and another observation is that if you do this, you take like these little sectors, they're contact handle bodies, and so you can apply this procedure. So the picture shows you a bunch of contact handle bodies, one to like in different colors, and they're stacked so that in time. So you have a first mushroom at the very bottom, and then when you go a little bit in the S direction, you have another one, and then you have another one, and so on. And I actually want an upper bound on the number of such things, and there's some technical stuff that helps you do some sort of stabilization, and you can show that you can get like an upper bound like 6. Okay. All right, so we have this, and let's think about the dynamics. So suppose you have something coming in from the bottom, and if you sort of encounter the large portion, if you counter the interior of this handle body, then you get sucked in. Now, if you don't, then you're over here, and then you get pushed around. Right, from this side's positive. You get pushed around, sort of in this direction. Okay, and then you exit. Okay, and then you go up. Okay, if you sort of in the middle of the interior portion, then you're already done. So the thing that sort of causes trouble is if you have something like this, goes up to the boundary, and then goes up and goes to the boundary, and then so on and so forth, right? Or things that are sort of, anyway, so the point is the following. You either get sucked in, or there's like a big thing, this thing, right? There's like a jaw of something that's waiting to eat everything that escapes. So there's intermediate things that are sort of, eating things along the way. And if you sort of escape and you think you escaped, there's like a big jaw waiting to eat everything that's left over. So anyways, there's some sort of procedure for making sure, no orbits escape. So anyways, that's the end of the proof of theorem A. Okay. So let me comment a little bit about some applications of our technology. So the first thing is that any almost contact submanifold can be C0 approximated by a genuine contact submanifold. So this is an existence H principle for contact submanifolds. Maybe I should say at the very bottom, in view of Gromov's H principle, the case that was previously unknown was the case of codimension 2 contact submanifolds. And also an alternate proof of this fact was given by Casals Pancioli Pressas. And since I'm running low on time, there's a corollary, so you can read it. And then there's one more strange remark. If you combine the first corollary with Gromov's H principle for contact structures on open manifolds, you can easily deduce the existence H principle for contact structures, and giving an alternate proof of the existence H principle due to Borman, Eliashberg, Murphy. So, so the sketch is the following. You have your contact manifold M, right? That you want a manifold which is almost contact, and you want to realize it's a contact manifold. Then you sort of cross. The obvious thing is like cross it with R2, okay? And this is going to be this is an open manifold, and it admits a contact structure by Gromov's H principle. And then now you just apply our wiggly thing, okay? And then like this, okay? And voila, this is actually a contact manifold. So you embed in, so you want to embed M inside here. The very strange thing is that it turns out that the Casals Pancioli Pressas paper actually uses PEM. So if you want to prove PEM using Casals Pancioli Pressas, you can't because it's circular. But somehow our strategy actually gives you a non-circular new proof of their result, which is actually sort of nice. Okay, I think that's it for now. Thank you very much for listening.